So we've seen generally how we can propose reaction mechanisms for first, second order reactions. And the steps that we can use to propose those are very simple. We can use the experimentally determined rate law to write that slow step, that rate determining step, as the first step, the first elementary step in the reaction mechanism. And then we just going to write additional steps, either one or more additional steps, so that whatever species we introduce, we cancel out to give whatever that overall reaction is, right? So that's the general strategy that we're going to employ. However, sometimes we encounter a reaction where the experimentally determined rate law is suggesting to us a very unlikely scenario. So for example, if we take a look at the reaction between nitric oxide and chlorine, so we're going to write out this overall reaction first for this example. So we have 2NO reacting with chlorine gas, Cl2, to produce NOCl. So 2NOCl. That's the overall chemical reaction. And then what we're doing now is this reaction is going to proceed. We're going to propose that is going to proceed by a two-step elementary reaction process. And the first step, NO reacts with Cl2 to produce NoCl2. And then in step two, the NoCl2 reacts with NO to produce NoCl. So what we can do, again, we can write out the rate law expression for both of these elementary steps. So before we write those out, other piece of information that we're given is that when we perform different experiments, we actually determine that rate law to be rate equals K times NO to the second power times Cl2. So what you will notice here is that the rate law kind of matches the stoichiometry for the overall chemical equation, which we said is not a general, we can't assume that, right? We need to determine this experimentally. So if this reaction, this overall reaction, were to actually proceed by one step, this would actually involve two NO molecules colliding with a Cl2 molecule simultaneously. So you actually have three reacting molecules colliding together, and that is probably not going to happen. That is very highly unlikely for all three of them to collide in the right orientation, to collide with enough energy. So what's actually more plausible is this reaction proceeds via a two-step process, which we have here below, the first step being the fast step, and then the second step being the slow step. So when we write the rate law, and again, we really just need to focus here on the slow one, but we can also write the rate law for the first one. So we can say the rate here is equal to K, and we have NO times Cl2, and we'll call this K1, sorry. And then for the second step, so we have the rate for the second step equals K2 times NoCl2 times NO, right? And this here is the rate determining step, of the slow step. So obviously, right, what we notice is that the rate law for the rate determining step is not the same. If I compare this to that, the rate law for the overall reaction, they are not the same, right? So there's something we need to consider. The other thing that we will see here is that the rate law for this rate determining step, it's written down here, it includes this NoCl2, which is actually, right, if you look closely at it, that's an intermediate. Okay, and your rate law cannot have intermediates in them. They should only have the concentration of the necessary reactants. So what then this suggests is that we need to invoke another strategy to help us explain what's going on and to propose what's going on in this particular reaction. So what happens, because we have a fast first step and a slow second step, if at the end of the first step, we're generating a bunch of this stuff, the NOCl2, right? So its concentration is going to increase. And because its concentration builds up, it's actually depending upon this NOCl2 now uh, breaking down or reacting with the NO to form the NOCl as a product. But this next step is very, very slow. So because it's slow, this concentration here, the NOCl2 actually increases, it builds up. And what it does, okay, it now forces the reverse reaction to happen. So now we have the opposite process occurring. So the NOCl2 builds up super fast, and because it's not used up as quickly, because the next step is slow, it starts to break back down back into the original reactants up here, right? So we can say there's a reverse reaction happening as well, okay? And we can have a rate constant associated with that, which is now K, to the opposite sign of 1, which would be K minus 1. And that tells us that process is happening as well because the concentration of the NOCl2, this intermediate, it builds up. It can't be used up as quickly in the next step because the next step is slow. So it starts to break back down back into the original reactants NO and Cl2. So this occurs, and this is what we need to now invoke to help explain what's going on with reactions that have a fast first step. So we have the NO reacting with the Cl2 to produce NoCl2 via the K1 rate constant. Then we have the NoCl2 going back this way via the inverse rate constant, K to the minus 1. So what happens then eventually is that we'll find that the rate of the forward reaction going from left to right ends up being the same as the rate going in the other direction from right to left. So we eventually establish what's known as a dynamic equilibrium. We'll talk a lot about equilibrium in the subsequent chapters. Okay, and at this equilibrium, this dynamic equilibrium means exactly what we said here. So the rate going from left to right, the rate of that reaction going in this direction, okay, ends up being the same rate going in the other direction where the NOCl2 breaks back down. So now what we can do is you can write those rate equations. So rate going in the left to right direction equals K1 times NO times Cl2. Okay, and then that is going to be the same as the rate in the reverse direction, where we have the rate is equal to K minus 1. So if we're going in the opposite direction now, going from right to left, this is going to be our reactant turning into the products. So now we're going to have K sub minus 1, and we have NoCl2 being the reactant. This coefficient there is 1, so that's 1 as well, right? So at dynamic equilibrium, these two rates, right, are equal to each other. So we can set them to be the same because that's what's established. So we can say now that K1 NO times Cl2 is now equal to the reverse, the rate expression for the reverse reaction, K minus 1 times NoCl2. Right, so we've set that equal to each other by reasoning and rationalizing why we have those rate equations to write in the first place, because we established that equilibrium, because this fast first step leads to a buildup of the NoCl2 that doesn't break down, that doesn't go into step 2 as quickly because that step 2 is a lot slower. Okay, so what this means then is we can now rearrange our equation. Okay, so if you remember, we wrote the rate equation for the slow steps. Let's back up here. And again, that slow step is our rate determining step. That's this one, RDS. And the rate here is equal to K2 times NoCl2 times NO, right? So we have this the concentration of an intermediate as part of the rate equation, which cannot happen. What we've just done in the previous step is we've come up with this expression right above that actually has the intermediate in it. What we can do now is a little bit of algebra on it. We can rearrange it and solve it for that concentration. So solve for the concentration of NaCl2. Okay, so if I just isolate this on one side of the equation, okay, do a little bit of mental gymnastics on this. We have our NaCl2 concentration being equal to, I'm just going to divide this side by k to the minus 1. I divide this side by k to the minus 1 as well. Okay, it's not that complicated. It's a little bit of algebra. So we end up with K1 over K minus 1 times the concentration of NO times the concentration of Cl2, right? So this entire thing is equal to the NoCl2 concentration. I can take this and substitute it now into my rate expression for the rate determining step into that equation. Okay, and I'm just going to try to keep my colors here consistent. So now the rate is equal to K2, and I'm substituting everything in purple in here. So I have K1 over K minus 1 times NO times Cl2, and then I have my thing left over in green. I have my NO as well. All right, so if I simplify it now, what I end up with is the following. I have my rate being equal to K2 times K1 divided by K minus 1. All of these are constants, right? K is a constant, whether it's K2, K1, K minus. So we'll say K overall for that, right? When we multiply a constant by a constant, we divide it by another constant. That gives us just a whole brand new constant, okay? And then if you simplify this side of it, right? NO times NO gives me NO squared. And then I have my Cl2 left over. Guess what I end up with? I end up with a rate law expression that matches now the experimentally determined rate law expression up here. We have a rate KNO squared divided by Cl2. What I came up with down here is rate KNO squared times Cl2, right? So that's how when we are presented with a situation where we have a fast initial step and then subsequent slow step, for instance, we can still write that rate equation for the rate determining step. We just need to do a little bit of massaging of the information for the fast step. Again, assuming that that is going to establish a dynamic equilibrium, and then writing the rate equations for the forward reverse reactions, solve for whatever the intermediate was in that case, and then resubstitute it back into the rate law expression for the rate determining step. We end up with the rate law expression for the overall equation with respect to the reactants in the overall equation, not with any of the intermediates. Okay, so we went through, several things there, and yes, there's a little bit of chemistry involved, but again, this is a common thread, especially throughout the initial parts of Gen Chem 2. There's just a bunch of math involved, right? And here we're doing a little bit more algebra and manipulation of our equations. Okay, so let's take a look at one more example. So we have the gas phase reaction. This reaction we saw previously between nitrogen monoxide or nitric oxide and oxygen to form nitrogen dioxide. And it says show that the following mechanism is plausible. So we have our mechanism down here. First step is fast, second step is slow, and then we're also told that the experimentally determined rate law is this thing. Let me rewrite this up here to the side. So we have a rate equals K, and this is a typo. This should be NO squared times O2. Okay, so that's an experimentally determined rate law. We need to show that this mechanism here is plausible, a reasonable way by which this process can happen, right? So we can write again our slow step here. That's our rate determining step. So we can write the rate law for that. So rate equals what we have K2 times the concentration of N2O2 times the concentration of O2. Again here, this N2O2, that's an intermediate. Okay, so we can't use that. It doesn't reconcile with the rate law of the overall equation. So now we need to use some information from this fast step. Okay, so we know then that the rate of this fast step in the forward direction, okay, it needs to equal the rate in the reverse direction. So we can write the rate in the forward direction, and that's equal to K1 times the concentration of the of the reactant. So we have NO and then we squared, and then the rate in the reverse going from right to left now would be K to the -1. And then that is, we have N2O2, and the coefficient there is 1. All right, we can set these two rate expressions equal to each other. So set them equal. So we end up with K1 NO2, I'm sorry, NO squared is equal to K -1 N2O2. Okay, N2O2 is our intermediate. We need to solve for this here. So N2O2, divide both sides by K to the -1. So K1 over K -1 times NO squared. We're going to take this now, entire thing, and resubstitute it back into this term and for the rate expression for the rate determining step. So we end up now with the rate equals K2, and I'm going to substitute everything in blue for what we said was N2O2 concentration. So we have K1 over K -1 times what do we have, NO squared. And then we have our O2 that remains. That's in green. I didn't mess with that. That didn't substitute anything in there. And if we set all of the rate constants here times each other being equal to the new rate constant. So you have rate equals a new rate constant K. We have our NO squared times O2. Okay, we can see now that the overall rate expression, I'm sorry, the rate expression for the rate determining step by doing a little bit of algebra is the same as the rate law expression for the overall reaction.